Well, thank you very much, Dan. Thank you, everyone else, for coming. It's a pleasure to be here. I was along with many others, in Montreal for the CAI conference, and this is some sort of homecoming. I did my PhD in Toronto. I'm a Canadian citizen, and so it's truly a pleasure to be here. So I want to use the text entry, which Dan mentioned, keyboard on a smartphone, as an example of how user interface is evolving in the era of mobile computing, as well as increasingly AI-first world. So this work, this overview talk. It touched on many projects, and this is a long list of collaborators. Some are colleagues, some were former interns and postdocs and PhD students, both at IBM and later at Google. So the mobile-first era of computing kind of took many companies as a surprise. It changed very fundamentally how users use computing technologies in many cases. In two charts, one is the growth of smartphones. They surpassed the number of desktops very, very early. The other one, there are many phenomena. One interesting phenomenon is that the gum sales has gone way down since smartphone took off, interestingly enough. Partly because when people stand in line checking out, instead of picking a gum, they are doing twittering or whatever on the phone, so they don't pay attention to the gum stacks anymore. So why smartphone took off so well and so fundamentally? And our field, everybody in here has made a lot of contribution to it that make it to this stage. The number one factor is advancement and progress in hardware technologies. That is just generally miniaturization of all kinds of hardware, ranging from CPUs to memory to sensor to everything that got much cheaper, faster, smaller, and better. So this was, on the left, it was me doing my PhD in Canada in the early 90s. In order to do my PhD, to program the projects I needed to do, it was about a $200,000 or $250,000 SGI workstation. Today, that's like 10 years later, this mid-range phone from Google was 3 orders magnitude cheaper. And if you look at the Wikipedia specs on every dimension of computing except size, it's much greater than the SGI workstations that costed 3 orders of magnitude more a decade earlier. So that's the fundamental foundation for very different user experiences. The other side is UI design. And a lot of UI design based on a great amount of creativity and more traditional design approaches to UI. There's also some of it is fairly based on science, mostly human factor science, about understanding user behavior, user performance, and factor that into design. So that's also made a difference. And I argue in the area of keyboard, it has worked exceptionally well. Last year, Scott Forstall, who was one of the early executives, led the iOS development in answering a panel situation to a Wall Street Journal organized panel. He argued that the initial iPhone, the only scientific part was the keyboard. Everything else was more common sense, logic-based development. And that's interesting for him to say that. Lastly, it is the increasingly more powerful computational or machine intelligence that is driving interaction. And it also brings a lot of questions. And keyboard is probably the first that's using machine intelligence at scale on every phone, which I will explain a little bit more in more detail later. So the rest of the talk, I'll focus on text input as a special case of mobile phone interface. Why text entry? It's for many reasons, but one reason is it's indispensable because mobile phones or any computing device is, first of all, used as a communication device. And you need text one way or another to communicate, either to search or to social networking or old-fashioned email. It all involves text. And text writing is also an important part of every turn of human civilization, starting from carving symbols on stone to paper and pencil to the industrial age that brought us with the typewriter, and then until recently, typewriter-based keyboard, and accordingly, the clamshell form of laptop is pretty much the dominant way of entering text. And then we begin to enter the mobile computing era. First started with the PDA, which arguably is the pre-era of the prehistory of modern smartphone. And that question already raised. This was about 15 years ago. This artist raised the question: what is the symbol we use to carve on another tablet after thousands of years? It's a very interesting area in terms of research and invention, because fundamentally, any text input method is just a coding method. It's just a form of coding. And the question here is that the coding has to be compatible with some sort of human factors, either in terms of performance or ease of use, or compatibility with users' movement, efficiency, or cognitively compatible with how humans think about input.
The tech world is buzzing over Apple's latest must-have gadget, the MacBook Wheel, a revolutionary new laptop that does away with the keyboard. Tech Trends reporter Jeff Tate has more.
Thanks, Andrea. Say goodbye to the keyboard and hello to the future of laptop computers. With the MacBook Wheel, Apple has replaced the traditional keyboard with a sleek, touch-sensitive click wheel. Apple CEO Steve Jobs introduced the product yesterday at the annual Mac Expo. Senior product innovator Brian Gilman says the MacBook Wheel will make typing a thing of the past.
At Apple, our philosophy is create products that are simple to use, and nothing's more simple than a single giant button.
Gilman showed me how the revolutionary new computer works.
Just open the Intuitype alphabet menu here, scroll to the letter you need, see? And center click to select it. Then click again to capitalize, and repeat this process for each new letter. It couldn't be simpler. You can also let the predictive sentence technology complete the sentence for you.
Gilman says the MacBook Wheel has also simplified the organization of files, so searching your hard drive will be a snap.
Just press both sides of the wheel concurrently and center click, and there you have an alphabetical listing of every file on your hard drive. Everything is just a few hundred clicks away.
Apple is calling the MacBook Wheel the most intuitive product ever designed.
Here at Apple, we like to think that we're giving customers features they don't even realize they want yet.
While the MacBook Wheel won't hit the shelves for another 3 to 15 months, many Apple users already have it on their wish list.
I'll buy almost anything if it's shiny and made by Apple.
Alex Zalbin was one of the lucky few to get to try out a Mac Wheel and spent 45 minutes typing an email to his friend.
I never really realized how much I hated keyboards until I saw this thing. I like how the email automatically says sent from a MacBook Wheel. That way people know you have one.
With a price tag of just under $2,600 for the lowest end MacBook Wheel, it is an investment. But the super thin laptop features numerous innovations like the new ultra thin Hummingbird battery, which can power the MacBook Wheel for a full 19 minutes before needing to be recharged. And the computer is virtually unbreakable unless dropped or hit. But Apple isn't resting on its laurels.
As you can see, even this imaginary text input method had many human factors involved, including the prediction that may or may not help the user. So in order to do this well, from a more scientific point of view, you need more systematic understanding of human performance and various psychological research to support such a program. So well before I came to the invention of shape writing or gesture typing, I began to work with many colleagues, particularly Johnny Ecott, to figure out what are the sets of regularities or laws of action when it comes to interacting with computers. And there's already one that's very well known called Fitts law that basically can predict the time performance based on a simple set of geometry factors of the task. So you know where the target is, you know the size, you know the distance of it. You can pretty well predict the average distance, average time it takes a user to reach that target. And once you know that, this way, you can do many interesting things. One of the things is that earlier in our work is trying to optimize the key location. Instead of using a QWERTY, let's say, imagine you can let every key to move around until they find the optimal position. In here, the optimal or the optimality is defined by the least statistical distance between two pair of keys. And this was driven at the time a PDA era. You use a single stylus. The single stylus travels according to Fitts law prediction. Therefore, you can optimize their location to minimize the total energy. And this keyboard layout is called atomic, which is an acronym, but also for the reason that you can view each key is an atom, and the entire keyboard is a molecule, and the atoms in a molecule tend to stay in a total minimum energy state. So if you heat them up, they will bounce around, but if you cool down, it will turn to converge on a lower energy state. And that's how we come to design this keyboard, so called atomic keyboard. But pointing or tapping is not the only interaction vocabulary when it comes to interacting with computers, especially later on to mobile devices. So we begin to look at what other ways you can use as an element of interaction. One element can be used is crossing. Instead of tapping on an object, you can cross a bar. So we call it crossing UI. Like if you think of traditional Fitts law task or mouse pointing, it's all about dotting the I's in terms of putting a dot in a constrained area. And crossing the T's could also be a way of interacting with computers as a basic element of it. So we build models out of crossing. We also build models for continuous trajectory-based tasks to predict, given the width of a path and the length of path and the shape of the path, how well we can predict the average time it takes for an average user to pass through that path. So those are more physical or perceptual motor rules and regularities we're trying to uncover in order to support, say, something like a keyboard design. But there's also important cognitive factors. One of the most important cognitive factor is learning. And this is also where the HCI field, which I sort of migrated to from more traditional human factors field, differ. That human factors field, traditionally at least, is more focused on high performance, but professional users, called HO, or human operator. But the HCI field has always been, from day one, more driven by consumer electronics, or consumer end user consumers. So therefore, the expectation is that people are not going to learn anything. You just should be able to look at the computer screen and know what to do. And the GUI interface is, in that context, a huge revolution that turns computer onto every desktop, was able to do that. But this is very much at the cost of, often at the cost of performance. So the challenge is that how do you put the two things together? That is, you accept the fact that people don't go through a training stage, but still progress in their skills, in learning, in using. So this is where one of the fundamental ideas to shape writing comes in. That is, rather than tap, like say, I want to write the word quick onto each individual letter, in use, you would realize that forms a trajectory. And this trajectory can be used by gradually tracing the letters, making a trace that passes through these letters to form a word. And the theory or the hypothesis or expectation was that over time, the keyboard will become less important as a guide, because the memory build up and it become more of a memory recall driven process where you can get to a stage of what I call shape writing. That is, the shape memory is the fundamental driver of the user performance. In actuality, it's always a combination of both. But the more you use it, the less you will be dependent on the guide from the keyboard, visual guide from the keyboard. So that was the ideal. But in order to do this, this is where machine intelligence or computational intelligence comes in. That is, in order to cross another target key on the keyboard, you have to often pass through other irrelevant keys. So you have to have some notion of decoding to figure out what the user really was intended to. And this is basically achieved by using a language model in combination with a spatial model, which we'll get into a little bit more details later. But around 2004, we begin to make a first version of this, and the iPhone came out in 2007. We launched it on iPhone. Of course, iPhone did not allow third-party keyboard at the time, so we wrote it as part of a writing pad application. And some users recognized it was a revolution even back in 2007. Some even wanted to give us a Nobel Prize if they were the ones on the panel. But nonetheless, it took much longer to get such a concept onto every mobile phone. Today, it's practically available on every single mobile phone, either iOS or Android. Then I joined Google, and we begin to think how this gesture typing and tap typing can be unified into one human factors and mathematical framework. And it turns out it's, in hindsight, conceptually, actually it's quite easy. And it's actually easier to talk about this in terms of tap typing or touch point typing. So basically, you can view every input of the user from the human finger as a sloppy, noisy input, but with some signals in it. And the output should be text, and that's decoded from the noisy input. And this is a classic Shannon channel, Shannon information channel. To decode this process, you need two pieces of knowledge. One piece is how humans make the spatial signal for a target word. Let's say I want to type the word THAT. What are the possible ways the human would express that? And that's what I call a spatial model. So basically, given a word, what would be that signal? So here is S is signal, word is the target. So we can build a model that estimates that probability distribution. For every gesture or every tap point, a set of touch points, that means that you can calculate the probability distribution in theory across all words that are legitimate. And then the language model will tell you, given the preceding context, if you say how likely the word you is. So that forms the prior. And the wonderful Bayes rule combines them to return the problem at hand. That is, given the signal, what is the word you want? And it works out just maximizing this likelihood of words based on those two pieces of knowledge or model. And that's arguably, one way or another, that's how all modern keyboard works. The designers or engineers may or may not realize it, but this is ultimately how they work conceptually. The question is that, what is the spatial model? So we have to go back to the human factors. Other than, say, Fitts law, we know it's one of them. But by then, we already know people don't use cursor or stylus to tap on a key. Rather, they use their finger. Turns out finger on a small screen doesn't quite follow Fitts law, because Fitts law fundamentally says it's the relative precision that determines the moment time. But on a touch screen, we know the finger is far wider than a key. So the absolute precision become an important, if not dominant, factor. So we have to remodel Fitts law to make it work for touchscreen, and that's another piece of foundation we built to this field. But furthermore, human typing behavior is actually a lot more complex than a single movement point traveling. For example, more people and more times today use two thumbs to type. and that movement doesn't quite follow Fitts law. And more importantly, the touch point distribution actually is very heavily affected by the hand posture. So if you use 2 thumbs or 1 thumb or 1 finger, the probability distribution changes. And all this can be potentially fed into how the decoder works, that is the spatial model. And we have done some research on this to try to get the nuance of the human movement out of the model so that it can do more precise decoding. But for now, given the technology constraints, we haven't measured worthwhile information gain to do that. So today, what we do is that every key is essentially treated as a generic key and the distribution is treated as a generic Gaussian distribution. And this is what I call the simplified or standard model of typing. So, and that comes nicely once you go fit that Gaussian distribution into the previous slides. You'll get a very nice, and then you take a log transformation for various reasons. There's a lot of nice properties once you take a log scale that essentially become a language model cost and a spatial model cost, which happens to be the square distance from the touch point to the center of each key. And you can calculate all words distribution, probability distribution, given the input you have observed so far. So, and that, the rest is a matter of finding more efficient data structure and algorithm to represent this equation so they can find the right word quickly in real time on a small phone for a large number of words. Like in English, it's about at least 100,000 words. And then the language model is a field of its own. How do you come up with a model that would, given what happened in the past, what is the distribution of the next word that you are going to enter? This can be as simple as a list of words, as the vocabulary itself is the simplest form of a language model. But it can be much more sophisticated than that. The classical language model, of course, is the Engram model. That is, again, how R, U follows how R by about 30%, and so on and so forth. And the rest of words are all, in theory, predicted by this language model, except rare occasions you cannot have that larger model, so you smooth it out and use this classic backoff, and so on and so forth. The big difference in commercial world is that who has the best source of training corpus. If you train this on the web, you'll get all kinds of advertising or non-communication kind of content, which is not necessarily as useful for communication, for writing. So, of course, the model size, the bigger the model is, the more precise it is, but then it takes more memory, it takes more computation. And today, increasingly, the issue of privacy and personalization comes to play. That is, the more personal that language model is, the more predictive it is for that person. But it also means potentially there's more privacy exposure. So that's the kind of trade-off we have to make. And now newer technologies like differential privacy or federated learning comes in to maybe there's a way to make the learning on device or preserve the highly private part of the user's history, but still extract useful information. There's various techniques to that. And here's one experiment we ran that with or without language model. But fundamentally, language model also means decoding. Without a language model, you cannot do decoding. That is, you cannot combine that with a spatial model. So, and that's still a keyboard. Like even today, often, every now and then you will see because there's also drawbacks to once you have decoding because it's not 100% correct according to the user's intention. And that could be infuriating. Like I meant this word, like say, I type AMD, the system will insist it's AND because AND is a word, AMD is not a word. And that kind of, if the user works for AMD or uses AMD, and that's very infuriating. So therefore, like even today, like last week, either Forbes or New York Times was giving user tricks about how you find a way to turn off autocorrection. But if you turn off autocorrection without a language model, what is the average precision? And this is the experiment we ran. So we ran that. Without that, we ran an imagined algorithm on, say, the unrun corpus, which is due to litigation, the unrun corpus published. The unrun corporation was forced by court to release its email history. Therefore, you have a real life history that can be repeated on every person, about 200 users over 4 years or maybe more time. So we deploy such a keyboard, either a dumb keyboard that doesn't do any correction, or keyboard with a language model, or keyboard with a personalized language model. An important part about the personalized language model is that it's a combination of a large language model trained on 100 billion words and that person's history blended, so-called a cache model and background model blended together. And you can see without any language model, you get, about almost 40%, where's my point? Okay, about 40% of the words are actually wrong. So people don't realize the artificial intelligence in a way is helping you at least 40%, about 40% of the time. You would have got it wrong without the help of a language model. You have a background model that reduces dramatically to about 6%. So 6% of words are going to be still wrong, but it's much less than 40%. And then if you use a personalized language model, it reduces to 4.6%, and so on and so forth. This is one experiment. The numbers may be not exactly the same, but this is the kind of computational simulation or experiments you can run to figure out what are the algorithm impact on typing. Okay. So more back to spatial model. I talked about gesture typing earlier. So what is the spatial model of gesture typing? And here, Fitts' law no longer, at least doesn't apply directly. So we begin to look at, a few years ago, Philip Quinn and I were beginning to look at deeper into human motor control literature to find rules that may apply to gesture typing. And one of the principles is the so-called minimum jerk principle of human movement. That is, the human movement may follow many rules and targets and goals, but one of the fundamental rules is that the movement always tend to minimize the third derivative of moment. The first derivative being velocity, and the second derivative being acceleration, the third derivative being jerk. So minimizing jerk, essentially minimizing the smoothness of a trajectory of a movement, which happens to be less energy needed and you can be more lazy about it. So using that, and a combination of that and Fitts' law, we were able, which dictates the via points, we were able to actually build a model which is computational and statistical. And that model can actually generate gestures just human-like. And we feed that set of gesture, as well as sets of real collected gesture to the recognition engine, you get about the same results. So as far as the recognition engine is concerned, it will be about the same kind of accuracy or difficulty of separating them out. So that's another example that that comes to how we can understand deeper into modeling or human performance modeling to help with performance with keyboard quality improvement. And with that, we will be able to do the kind of longitudinal simulation experiments of unrun corpus or any real writing history in the same way as we did for tapping. So here is an example of
WatchWriter, a finger-operated keyboard that supports both touch and gesture typing with statistical decoding on a smartwatch. Just like on modern smartphones, users type one letter per tap or one word per gesture stroke on WatchWriter, but in a much smaller spatial scale. WatchWriter demonstrates that the combination of human motor control adaptability with modern statistical decoding and error correction technologies developed for smartphones can enable a surprisingly effective typing experience despite the small watch size.
So that even surprised us. That is, can you apply the statistical decoding on a much smaller form factor? So there's a scaling effect to both the human movement behavior as well as to the recognition engine. It poses much more burden on the recognition engine to recognize more gestures that's closer to each other. And we were totally blown away by the results, even ourselves. Initially, we said, well, put a keyboard on a watch, got to be crazy. Because the finger is about at least three or four key width. So it's highly ambiguous, but the systems can still decode it. And this is an example in comparison to more traditional HCI techniques where you have to resort to essentially multiple steps. That is, let's say in order to enter a word, you first amplify the keyboard, you type once, the keyboard rooms up, you type the second time, you get to it, or you shift the keyboard around, only part of the keyboard get exposed to the watch interface, then you'll be able to resolve it by human level of resolution. And that is fundamentally slower because it operates at a much lower level of operation. And this is pulling data from other papers, but more or less in the same ballpark, is that traditional techniques can get you but 10, 15 words per minute. But this approach, this is machine intelligence and human factors-based approach from the start, will get 20 or 25 words per minute. So you'll notice that earlier I talked about the atomic layout. That was optimized for minimizing a single point traveling distance fundamentally. Or you can say it's minimizing the Fitts law time, or what I call Fitts digraph energy. That means Fitts law weighted by the digraph or the transitional frequency from one letter to another. But in practice, so far, with one exception, we did an experiment in the initial ShapeWriter application on iOS that some people did learn this atomic layout. Most of it goes back to QWERTY layout. And the QWERTY layout happens to be particularly bad for gesture typing. And many folklore says it's actually also bad for touch typing on typewriter. That's generally, there's some truth to it, but it's not that much truth to it. The truth was that Christopher Scholes and his colleagues in 1860s had no idea how people were going to type. They didn't think, the very notion of typing without looking at the keyboard was not discovered till about 30 years later. That is, in 1890s, that people realized you don't have to look at the keyboard. You can learn so-called touch typing with 10 fingers. And secondary schools did not start teaching typewriting, touch typing till the 1920s. So they had very little notion of human factors back in the initial invention of typewriter, which was actually the 52nd invention of typewriter. There's many other inventions before that. But Christopher Scholes was mostly driven by, and his colleagues was mostly driven by the need of not getting the wooden word prototypes jammed together. In order to avoid that, they did this trial and error to say one key comes from one side, the next key is likely to come from the other side, so they don't get two hammers get jammed together. That was mostly the motivation. But except when it comes to shape writing, it's a very highly ambiguous keyboard. So for example, if I want to type the word OR or OUR on QWERTY, it's the same gesture. There's no difference whatsoever. And many other words are like that too, like tip or top and so on and so forth. And other words are more similar. It could be just one pixel difference that will become two different words. So we try to find a way to, going back to the original vision of shape writing, to make the keyboard more clear. So the objective function is not only speed, but also maximum clarity. So statistically, two word shapes are least likely to collide with each other. And that's one dimension we begin to look into. And this is still unfinished work, and we're still working on this. And that's a plot showing using a sophisticated optimization technique. You can find each point on that top right corner is a keyboard design. And you can have a large number of them, and they form a so-called frontier surface. And you pick this one on the surface according to different dimensions of goodness. Let's see how I'm doing with time. Okay. I need to speed up a little bit. So far, I've been focusing on essentially error correction. That is, from a noisy or ambiguous or even erroneous sets of input, how do you decode it into the right set of intended words? Another use of the same technology is actually fundamentally exactly the same. That is, before you finish writing the intended text, the partial input is casted into future to see how likely. I already see some percentage of time you are typing on THA, and how likely you meant the word THAT, and so on and so forth. And so often this is more visible part of intelligence. That is, it does auto-completion for you. And that actually has been a technique in accessibility for decades prior to smartphones, and also a technique in some sense in Chinese or other non-alphabetic writing systems as well. That's just necessarily needed for decoding. But its cost and benefit is still not well understood. For example, today in Android, in iOS, we also do app predictions. So you use one app, how likely you're using Twitter, how likely next app is Instagram, or what relationship they form. If you can 100% predict the next app or function you need, why don't you just give that function or at least list that function? But so there's a lot of benefit to be gained if we can precisely predict them. The question is that what's the cost of not predicting them? What's the cost of predicting them wrongly? So here we did one experiment just in case of keyboards. Keyboard today, almost all keyboards, including iOS does 3 suggestions. That's starting up more on the Android side. So hopefully one of the 3 suggestions, as you type just, let's say in this case, SUB, they give you a suburb, a subject, or subway as one of the choices. And hopefully one of them is what you needed. But the cost, the human factors cost, is that first of all, none of them might be what you expected. And then you spend time looking at it. That's a cost. Even if it is, one of them is what you needed. You need to make a decision. First of all, it's there. Second of all, it's sort of a Higgs law-ish kind of a reaction time to determine which one is the right one. And then you have to make a motor action to select it. So if I typed T and H, it predicted THE. So then I select THE is another action. I may as well just do the THE. So indeed, we simulate state-of-art language prediction, and we found make it as favorable as possible to the prediction. In terms of time, people always lose. Not always, but on average, people will lose. The more you use suggestion, the slower you actually enter words. So and that's quite interesting, and that's an interesting question still to be figured out. That is, what are the true costs to the user? Because it does save users effort. The user will take less number of actions. So the number of keystrokes can be saved up to 40% or 50%. Now we have something like smart reply, which is much longer than prediction. Like before you even write anything, Google thinks you want to say, thank you very much, or I'll see you tomorrow, or yay, and with an exclamation mark, based on the incoming message. So there's much longer span language model prediction. And how we think, reason, and analyze and calculate the cost and benefit is still to be worked out, in my view. So let me just point out where we have been and where we're going. Again, keyboard is just an example of how mobile HCI or HCI in general may move. In my view, it will move more towards the direction of a combination of AI and human factors. The AI part is deeper, larger machine intelligence based on large amount of data and based on deep learning. On the human factor side, the more we understand the human behavior, the better we can utilize that information and construct better technologies that would enable the user to express themselves in the least effortful way. With that, I thank you for your attention. I'll answer some questions. Yeah, it's okay. The question is that, I think there's a specific question, but the general question is that when we talk about different models or different decoding algorithm or different UI design, we talk about a percentage of improvements, but is that percentage perceptible to the user? Like, at Google, everything we do is based on some sort of metric. And the metric, if you can make a 1% difference to Google search, for example, that's huge. That's a huge amount of achievement. But is that something user noticeable? And that's a very deep question. There are many answers. You can also say there's no answer because it all depends. So you almost need another lecture or many discussions to resolve that. But I will share just a few things that come to my mind. First of all, these differences are nonlinear. So speech recognition, up to 5 years ago, was at around error rate around, say, 10 or to 15%. And the whole achievement in the past 10 years was tremendous. A lot of it come from Canada, the fundamental inventions. That makes it to something like, say, they say, let's say, 50% error reduction. 50% error reduction is relative, meaning from 10 to 5. But that is 5% absolute, but somehow reached a qualitative difference. That is, you find out speech recognition is practical. So there's that hurdle. But still, there's occasional errors that's still infuriating. So it depends on what stage it is. The other side is, human may not notice. Often people don't actually appreciate the benefit that machine intelligence provided until you take that away. Let's say the experiment, let's say last week New York Times suggests, well, this is the trick where you find a way to turn off autocorrection. You turn it off, you realize, it gives you full of 40% of error, and then you realize, that's actually helpful. Same is true to many other dimensions of intelligence. So I'm sure you may have other dimensions that comes to your mind, but this is indeed some of my colleagues and my own team also study this essentially asymmetry in human judgment, and that's well known in human factors or psychology. The people has asymmetrical estimate about gain versus loss, like the famous Nobel Prize winning experiment on, let's say I'll give you two prospects. One is that I'll give you, say, $50 for sure, or we'll give you $100 versus 0. So I'll flip a coin. If it's head, I'll give you 100. And if it's tail, I'll give you 0. Most people will take the sure bet. And so people are fundamentally conservative or risk averse when it comes to making gains, making profit. But if they already lost like $50 in the stock market, they want to stay in there. Hopefully it will return. So they become more risky seeking. So there's the asymmetry and all that. So when it comes to HCI, it's very much the same. That is, when you make an improvement, they generally don't realize or appreciate as much as when there's a cost to it. And this cost, what is the right trade-off? And we actually constantly struggle with this kind of decision. For example, in the keyboard, I didn't have a chance to go to the details. It's actually very principled. The so-called standard model is very principled. That is, it's actually from a Gaussian distribution, you can exactly estimate what is the cost, what is the rational weight on language model prediction versus their spatial model input weight. And that weight is not arbitrary. It's basically it's proportional to the standard deviation, to the deviation of the Gaussian distribution. But in actuality, that might be just too much. People don't like it. So we generally, if you type AMD, you wanted to type AMD, and the result is AMD. In our internal test, we gave us 10 times penalty as if you meant for AND and you changed AMD to AND. So for every loss, we have to make 10 or more wins to justify the algorithm tuning. So it's a whole new topic, and yeah, it's a big part of it. Thank you for that question. Yes? The question is that what about people with certain types of motor impairment or like Parkinson's disease and so on and so forth? Would that be, should we do something specifically for them? The answer is yes. Are we doing it? Not yet. Why not? We don't have enough technologies. Maybe actually that's a good, maybe we can tune them. There are some researchers doing this. Basically, you make a special spatial model for them, and different diseases may exhibit different behavior. Let's see if I can find a slice on a similar topic. Let's see. Yeah, this is it. So from that typing posture paper, we know that if you type with the right thumb for a letter on the right side of the keyboard, interestingly, you're likely to land, say if you want to type a letter L, you're more likely to land either on the edge, the right edge of the L, or even further away. If you type with a finger, you are more likely to be lower than the key. Maybe because people want to make sure they are approaching the right target. So generally, there's tendency to lean outwards when you type with a thumb, and lean downwards when you have typed with a single finger. And it also depends on which part of which key and all that. So potentially, we can have a model that factors that person, the hand size, the location, and which finger you use. You can factor all of this in to build a spatial model just for that. The trouble is that the same user usually type with a finger and now hold a cup of coffee, decided to type with one thumb. And if you build a model for the finger, then it's actually worse than a generic model for thumb typing. So we have to develop a method called hierarchical spatial model backoff. So when a system is confident that you are doing finger, it will go to a more specialized model. Otherwise, we'll go to a generic model. And that, it always starts with a generic model so that there's no loss. It's always win. And we actually built this very sophisticated model running on a language model and did experiments. At a letter level, you'll make obvious improvements. But once the language model kicks in, most of them are absorbed by a language model. So there's no practical, not enough again, to make this kind of techniques worthwhile. But it may become more worthwhile if we have more signal to say, definitively, you are using thumb or you have certain motor tremor. If we factor that in before you start typing or as soon as you start typing, or on every single touch point or every gesture, then we'll be able to do better, perhaps. So we're just not there yet. But on the other hand, gesture typing alone was already very helpful for many type of motor impairment. One of my most satisfying professional experience was when we launched ShapeWriter on iOS. Someone wrote to us an email saying, well, her daughter, due to some sort of a motor impairment, could not type or speak very well for the speech recognizer to recognize her voice. This was 10 or 15 years ago. But she downloaded ShapeWriter, she could type, and it could communicate with others, and that changed her life. and her mom said, and ours, and the parents' life as well. And that was most rewarding experience that I received. Yes. So what are the dimensions of optimization for shape writing or keyboard in general when you do optimization? That's a great question. There are many. As I alluded to, in early days, if you think not thinking shape writing, just think one stylus traveling. It's simple. It's just minimizing the traveling distance. That's simple. And statistical distance. So factoring language model factor as well. But when it comes to, say, change the layout, we fundamentally also think about what's the average statistical clarity. And that's not the same dimension as distance. So we have to look at least those two distances. The most difficult one was the third dimension, is what layout is easier to remember, easier to learn. And that I still have no clue. And yesterday I was talking with a colleague at Kai, and he said, there must be ways to think about what shape is more learnable than other shapes. I'm not sure. I'm skeptical. I'm skeptical in the sense that if you factor it in, that will be a too tight space to actually for optimization. We already are in a very pretty tight space. In the past, we thought about similarity to QWERTY is actually a good metric for learning. Not necessarily because QWERTY is easier or better for learning. It's because most people have already invested countless number of hours learning QWERTY. And making keyboard similar to QWERTY will give you the advantage of prior learning and also the visual search behavior. We have tried that, but we published many papers on that, including a minor tweak, like say, if you change the letter I and J, because letter I is neighbored by U and O, two other important vowels in English. We know words are all made up around vowels, so therefore a lot of words will travel to the top right corner of the QWERTY keyboard. And if you just move the I downwards one and swap with J, all of a sudden the keyboard increase something like 10% clarity. But it still is a learning that takes like a week or two to get used to. So we're still facing a trade-off. So that's a whole new topic. Old topic in a way. I'm still pursuing with many colleagues to say what are the best way to get people to learn things. So there's our many dimensions. But it's also there are many other nuances. We can talk more offline.
Great, thank you, Shumin.
Thank you.